I'm recording this. All right. Amazing student. So, first I want to check in. Do we have any concerns about what we addressed yesterday? So I know that we reviewed how we can get the enthalpy of the reaction. It was after we took a test. I know our endurance was waning. Are there any questions? We'll keep going back to that. In fact, some of the unit assignments, so I've already communicated which ones that we can take care of. And remember, that's the pink packet. And as of the end of today, you'll be able to answer 2, 3, 4, just to show us, you know, what we are actually learning as we go. 8, 11, and then the first free response, you can knock out A and B if you want, and the second, definitely A. Just letting us know where we'll be by the end of our time today. Okay, any questions on what we addressed yesterday? Then, where we're going to begin this entropy thing. All right. So this is the terminology that we want to be using. So I'm not sure if this term has come your way in other science classes or math class. Okay, we need to use this terminology. So what does this mean? All right. So the old high school auditorium, were we all in that at one time? Yeah. Okay. So let's say that old high school auditorium that we're going to send Brendan there. I assume it's still as it was. We'll go back in time. We're going to send you there. Now, we're going to ask you to take a seat. Remember, there were 3 sections. We're just talking about the main part, not the back. Well, you could choose to sit in this first seat, or the second seat, or the third seat, or we could go on and on and on and on and on. Those all, having you here, Brendan, or having you here, is a different microstate. Now, what if we sent Brendan and Connor? Well, then Brendan could go here, Connor could go there, or vice versa. Well, couldn't Brendan go here? Connor stay here. That's another microstate, and on and on and on and on. Okay. Our new auditorium, we know, is larger, has a greater number of seats. So the possible arrangements of where Brendan by himself could sit versus this has a greater entropy. There are more possible positions. So we would say this has greater entropy because it has a greater positional probability. You know, usually like certain terms aren't set in stone, but these are. Or the greater number of microstates. Okay, so just to exemplify this further, on the back of this page, I colored these to make it a little bit easier. So you guys who have had statistics or not, I'm sure just taking a look at this, maybe this will help drive home what entropy is. Okay, so imagine that we have some kind of a vessel that has 2 bulbs that are connected by a bridge. And so if we have a gas particle, the gas particle could be here or here. We're going to ignore the bridge. Well, if we have a total of 4 gas particles, and yours are labeled, it's hard to see, A, B, C, or D. That's why I made them different colors. So I made one red, can't remember which one blue, and on and on. Okay. Well, to have all four in the left bulb, well, that's going to only deliver one possible arrangement. That's it, right? To have all four in the left. Now, of course, this could be here and this could be here. If we're assuming they're gases, they're not going to be still. So we just say they're all in the bulb. There's only one possibility. Well, how about all in the right bulb? Well, there's only one possibility. How about 3 of them in the left and 1 in the right? Well, since there's 4, then I need to show one of these with red in the right, 3 on that side, 1 with green, and so on and so on. How do we know? How do we know that we're going to have equal numbers in both bulbs? How do we know that? So we know how gases behave. And gases have very high kinetic energy. In fact, their kinetic energy is much greater than the particle attraction, right? Oh, yeah. So what we say up until today, well, a gas expands to fill its container because the kinetic energy is much greater than the particle attraction. But what a thermodynamic chemist would say, well, to have two of the molecules in each bulb is favored because that's the greatest state of entropy. There's the greatest number of microstates, or this situation delivers the highest positional probability. And we'll keep referring to that. So if we go back to the auditorium, well, let's say we give Brendan a balloon to take with him. And we ask you, sir, to pop that balloon when you're in the auditorium. We know what's going to happen. We know that whatever gas was inside of here is going to travel. We're going to have diffusion, et cetera, et cetera. And it's going to now be in this new container, if you will. Why? Does it have much higher kinetic energy than the particle attraction? So they're going to use that to expand. But thermodynamically, we would say, well, when the gas was in here, when it no longer is contained, it is not going to stay there because there's not as many possible arrangements as in the larger volume. It expands to fill the entire volume because the larger volume has higher entropy because there's a greater number of microstates or a greater positional probability. Yeah. Okay. So could we do some really simple kind of applications? If we turn to page 4, please turn to page 4. Okay, so all that you're asked to do is just choose which of the 2 samples would have a greater entropy. So can we take 30 seconds? And we want to make sure that we know why. So I think it's pretty easy. The one that has the greater entropy, the gaseous, and then the nitrogen at the lower pressure. Why? Well, in a solid. So carbon dioxide, just to remind us, nonpolar, it's just going to be out by London dispersion, but in the solid state, it is held in place. Yes, very little kinetic energy. So If we have a molecule here, it's pretty much staying there. Here, it's pretty much staying there. And just a little bit of vibration. Where gaseous carbon dioxide, we know naturally there's going to be motion, and in and of itself, it is delivering greater number of arrangements, greater positional probability because of its behavior. The 1 atmosphere versus the 0.01 atmosphere. Well, what must be true about the nitrogen to have such a low pressure? I guess we assume they're about the same size, mass-wise or particle-wise. Well, we would assume, oh, sorry, very big volume. So again, do you have the gas trapped in a balloon? Then we're going to have a lot of collisions, high pressure, or is it in a larger container? And where the nitrogen could choose, you know, one might be there, one might be there. Not that it's choosing, but we understand. Okay. So usually we are not just judging like, okay, the solid state or the gaseous state. Usually we're looking at transformation. So iodine vapor condenses on a cold surface to form crystals. Actually, it would be deposits. Because if we're going from gas to solid, that's deposition. Okay, so this is what we start and this is what we end with. So are we increasing or decreasing entropy? Alan, you got it. So to say like the process, it's the change in, we decreased. Sugar dissolving in water, Joey. Increasing entropy, decreasing entropy. Ah. Do we need to talk about why that is? Gasoline burned in air. Gasoline is a mixture of different hexanes, many different ingredients, but we could just say mixture of hexane, burned, combustion, not balanced. Liquid and gas, all gases. Now, we need to balance it. Combustion reactions require a lot of oxygen, but the hexane plus the oxygen, I'm sure, will not be equal to the amount of moles of gas that we're producing here. What were you going to say, sorry? Positive. Because we're creating more moles of gases. Okay, what is the whole point of, you know, making these judgment calls? Remember the second law of thermodynamics that we looked at. The second law of thermodynamics, that was on page 5. Page 5. Remember, laws just tell what, not why. So it just says, okay, our universe tends toward the direction of greater positional probability. Do you know the old term? We cannot say this out loud or write it from this point on. The old term. So previous to about 10 years ago, we used disorder for entropy. Disorder. That's like a no-no now. So we may see disorder in our current textbook. We say positional probability microstates. So this is, in essence, saying is the disorder of the universe is increasing, just like my desk as the day goes on, or my nerves as the day goes on, or the drawer of silverware favors disorder, favors greater positional probability or number of microstates. Okay, another term though, Okay, back to page 2. Sorry, we're flip-flopping. Well, not sorry. You know what I mean. Okay. We've gotten this before, but to be totally 1,000,000% clear, you will be asked, is this process spontaneous or thermodynamically favored? Those are 2 of the same phrases. So spontaneous, aka also known as thermodynamically favored. Okay, well, what does that happen? What does that mean? So we could use either of those terms. And if we're asked, is it spontaneous? We need to know what it means. Thermodynamically favored, we need to know what it means. These are used interchangeably in questions, and you can use them interchangeably in answers. All right, what does it mean to be spontaneous? The process occurs without any outside intervention. The process occurs without any outside intervention. My desk gets messy as the day goes because I move when I teach, I pick up papers, I put them down, so that happens. I need to be conscious and say, okay, I'm going to keep all my AP papers here and all the papers I need to get back to the students here. And if I give it back, I need to then put it back in this pile. I have to do work to oppose what naturally is going to happen. My cup of coffee naturally decreases in temperature. I have to put in the microwave or have it on a heating element to keep at a higher temperature. Brendan, if you could have a plate of food right now, what would you like?
Traditional breakfast, eggs, peas, potatoes, and some bacon.
Okay, so the bacon, how do you like your bacon? Do you saute it? Do you microwave it? Do you bake it?
I like cook on the stove.
Okay, very good. Now, that process is not spontaneous. You have to invest heat, and you know that if you pull away the heat, the process is not going to finish. Yeah? And imagine raw bacon. Blech. So, oh, sorry if that is your thing. Because of course we assume cooked. Potatoes cooked. Yeah. So we have these throughout our world. Well, the question always is, will it do its own thing? Well, then we want that. Then we don't have to spend any effort investing heat or electrical energy or anything else. Okay, so what decides if a process is spontaneous? There's actually 3 things, but for now, if the enthalpy of the reaction is negative, exothermic, we just make that observation in nature. Now, of course, we have to invest activation energy, but then it just goes and goes and goes, right? Once you light your bonfire, it goes on its own. You don't have to do anything. And the other thing, and remember those are standard, we can say standard state or whatever. And also if the process increases entropy, bless you. So we're decreasing enthalpy, increasing entropy. So if we would just judge spontaneity based upon the sign on the change in entropy, then we would say, oh, that's not thermodynamically favored. Process A. Ooh, that is thermodynamically favored as far as entropy goes. And that's thermodynamically favored. Yeah? Yeah. All right. So incredible students. Okay, in our green packet, please. All right, could we take a look at number 10? I meant for that, for your elbow. I know you were thinking in your head, yeah, sorry. That's where I am. Vibrant. Your eyes were glazed over, dude, but you were just in your head. Yeah, I'm not gonna throw stuff at you. That's what I need to do. I'm sorry. But I knew problems. I'm gonna take it for sure. And it's just baby Groot. Baby Groot's mad. Joey, pay attention. Which of these is an increase? Okay. How do we evaluate reactions? First and foremost, I would look at phases. If we are going, we know that solid compared to liquid compared to gas, we increase positional probability compared to the solid state. Everything, because of particle attraction, is held in its place. You're not going to get much movement. Here, particles are exchanging place. So this has a greater entropy. Gas, the greatest. So entropy is increasing as solid, liquid, gas. So, that doesn't help us here. We're not going from like solid to gas. So if everything is in the gaseous state, we look at, well, are we creating more moles of gas or less moles of gas? More, then there's more particles that then will deliver a greater number of arrangements. So if we take a look at D, now we're not looking at the formulas, we're looking at the phases and then the coefficients. So it doesn't matter, we're forming N2O2 from NO. No, it's phases and then amounts. That's a decrease. How about here? That's a decrease. Crystallization, decrease. We're forming solid from dissolved ions, boiling of water. That's it. Liquid to gas. Is that okay? All righty, Rudy. So in our packet, amazing students, could we take a look at page 9? Page 9. I know we're flipping around. Don't worry, we're totally fine. I transformed and modified this packet. This is an improvement upon past packets, but I just borrowed pages and wasn't cognizant. I just know numerically they're in order, but there will be numerical numbers missing. That's why, because I refined it. You're getting the best packet that I've given thus far. All right. So whenever you're a chemical engineer and you're proposing a new chemical reaction to produce aspirin, to produce rubber, to produce vinyl chloride, et cetera, your boss is going to say, well, how much is it going to cost? Yeah. Okay. Well, one of the things that's analyzed is the change in the process, just like we looked at. All right. Third law of thermodynamics. So we'll get there relating this, I promise. Okay. We learned how to judge the sign, but can we actually calculate a value? And we can. So laws just tell what? Laws just tell what? First law, energy of the universe is constant. Or talking about heat, can transform forms, but two, that the universe is tending toward a higher entropy. Third law, a perfect crystal at 0 Kelvin has no entropy. Now, that very first term should make us realize, okay, what is a perfect crystal? Every single ion or atom or molecule is exactly where it's supposed to be. Exactly. How likely is that? Not so likely. And what temperature are we talking about? Absolute zero. When there's no motion of matter. So we're creating conditions just so that we can say, okay, under these conditions, if we have water, if we have oxygen, if we have carbon dioxide, if we have methane, if we have sodium chloride, well, the entropy of that is going to be 0. There's no movement and everything's in its place. Okay. Then what we do, okay, if we look at the very back of our packet, on purpose, I placed this appendix at the very back. Okay, this is from your textbook. If we ever need these values, they'll be shared. Okay, chapter 6. And we reviewed this yesterday. Enthalpies of formation. And we know, okay, if we are forming, aluminum oxide, 1 mole of it, from its elements in their reference form at standard state. And so we would get what, 3/2 and then 2. That's how we get these values, right? And notice the units, kilojoules per mole. And alphabetical. Check out the farthest. Okay. No change in. These are assigned, referencing the third law of thermodynamics. Okay. So for example, we would take Al2. Oh, I read the formula wrong. Very sorry. Oh my gosh. Anyway, okay. We would take this formula, this compound, and say, okay, it's 0 Kelvin, the entropy is 0. All right, now let's get it to standard state. And remember, that's 25 degrees Celsius, 1 atm of pressure, and if it's a solution, it's 1 molar. And then this gets assigned. Okay, they are absolute entropies. Get the units. What a pain in the side. These are joules. So we have to be careful with our units. And they put it in joules, so they're just, workable numbers. If we take a look, there are no zeros. We're only 0 at absolute 0. So if we scan down, let's see, let's get to our first, So if we take a look just at the right column on this first page, take a look under carbon. Does it make, well, the crystalline structure of diamond is a bit more ordered or has less positional probability than in graphite. But look at, these are solid state versus gaseous. Do we see how much more entropy usually, goes along with gases? So CH3OH in the liquid state versus the gaseous state. Right? All right. So again, we're trying to get, well, how do we actually calculate values? Alan, I know I'm going to win you over, sir. Yes, ma'am.
Are those values called the standard entropy of formation? Or
No. Notice they don't have that little F. They're absolute entropies. So what that means is they're assigned just like. Now it's based on experimental evidence. Based on experimental evidence. So it's not like we just totally made it up and it doesn't have any backing. But electronegativity, that's a concept we've made up to explain the behavior in bonding. And we measure fluorine and then assign it a 4.0 based upon that. So it's the same kind of thing. They're assignments. They're assigned. Okay. So Alan, again, win you over, sir. So what we can do is pull those absolute entropy values and do a summation to get the change in entropy for a reaction numerically, not just the sign, numerically. Okay, so can we flip over to 11? Okay. Abrielle, would you do us the honors of please finding the absolute entropy value in that back appendix of NIS? And Olivia, would you mind finding the absolute entropy value for O2? And Gabby, do you mind finding for SO2? And I'll find for nickel 2 oxide.
so two is 240.
Thank you. Say again. Thank you. Go ahead. Okay, and again, just to like observe, it makes sense that the solids are lower entropy values and then the gases are higher. All right, so to get the change in entropy, we would sum up per the moles of product. Now it's not delta S. Yeah, this is product minus reactant. All right, so just being careful. 2 moles of SO2 times the 248 joule per Kelvin mole plus 2 moles of NiO. Sure. We do our math. Yes,
Why isn't it just joules per element? Not multiplying by moles. What I get from.
okay. I totally get what you're saying. Absolutely. I think I'm just bringing to our attention. You are absolutely right. Justin, you're absolutely right that these would cancel that and these would cancel this. Whenever we present the change in entropy for the reaction, just like we do enthalpy for the reaction, it'll be a certain amount of kilojoules per mole reaction, reminding us that it's per the balance equation. And so I'm so sorry. That was just habit that I keep it because I know that it means per mole reaction. Thank you for reminding me to point that out. Now, hold on. We're almost done. 20 seconds. Does it make sense that the change in entropy is negative? Why?
Because we're going from that more grams of gas, not more moles of gas to less moles of gas.
Wonderful. And we have solvents reactive cells as a product. We have 2 moles of 2 moles, but it's more the gas. Wonderful. Yes. So we would anticipate a negative change in entropy. Okay.